Okay, we saw different types of transducers based on their characteristics, namely resistive, capacitive, and inductive transducers. Starting from now on, we will learn about miscellaneous transducers. In that, we are going to first start with a transducer called thermocouples. The A thermocouple has two dissimilar materials A and B, and joined at a point, and this point is subject to a temperature theta degree centigrade. Then there would be a voltage developed across the terminals A and B. We call this as thermoelectric voltage. The thermoelectric voltage occurs mainly because the materials have different work functions. A work function is the energy that is required to liberate the outermost electron in the metal. So if we assume that work function A, energy A, is greater than work function B, then for a given thermal energy, the number of electrons in B will be greater than, so I have more electrons here and I have less electrons here, so this will become positive, this will be negative. Uh, this is an electric potential. Of course, that's a kind of a layman's explanation, because let's assume the work function is 3 electron volts, and I give 300 electron volts as input. There is no guarantee that I will generate 100 electrons, because if I give 300 electron volts and each 3 electron volts can liberate 1 electron, so I can assume that it will generate 100, but it doesn't happen that way. It could be there is only 1 electron generated and the rest of 297 electron volts is absorbed by that electron, and it simply converts it into kinetic energy and just zooms out. That is also possible. So this is a very complex phenomena, but in general, if EWA is greater than EWD, we can say that there would be a thermoelectric potential generated. So this was actually discovered by a German physicist called Seaback. So we call this as Seaback effect. So if I look at the characteristics of temperature versus output voltage for a typical dissimilar material, we will get something like this. It's more or less linear for many combinations, and I am talking about 0 degree centigrade to increasing, because 0 degree centigrade is not absolute zero, it is 273.16 Kelvin, so we will have some voltage. So we call this as VAB at 0 degree. So if I want to measure theta, then I need to subtract this offset so that I can get a characteristics something like this. This is what I want. 0 degree centigrade gives me 0 volts, 100 degree centigrade maybe gives me 100 microvolts, and so on. These are small voltages, normally few microvolts to few tens of microvolts, not very large, but still they are quite useful. So what I do is I take the same B and A. Now I keep this terminal at 0 degree centigrade. Then the voltage available, I call this as V0. This will be V0. So at 0 degree centigrade, the voltage, whatever is generated by the AB here will be cancelling with this. So at 0 degree centigrade, V0 will be 0, and as I keep increasing the voltage, I will get a very linear characteristics. Uh, this aspect of cancelling the residual voltage at 0 degree centigrade is known as cold junction compensation, because 0 degree centigrade will be cold, so we have cold junction compensation. So now I will get a very linear characteristics. People have uh, researched over the years, and they have found different types of materials that give you nice characteristics. And these materials, this combination of materials A and B, are given a letter. So you have thermocouples normally given in terms of letters. For example, we have the E-type thermocouple. The E-type thermocouple has a temperature range of minus 200 degrees centigrade to 900 degrees centigrade, and uh, uh, the metal is actually nickel chromium versus nickel aluminum. This is called chromal, this is chromal aluminum. So there are different types of thermocouples. For example, we have the J-type thermocouple, which goes from 0 degree centigrade to 750 degree centigrade usable temperature, and the uh, material is iron, and constant, which is nothing but copper and nickel. Uh, so this goes, as I said, 0 degree centigrade. Again, depending upon the different types of thermal, the J type and E type. E type has about 0.7 degree centigrade error. This has about almost 2.2 degree centigrade error. So there is another type, let's say T type, which goes again minus 250 degrees centigrade to uh, 350 plus 350 degrees centigrade, which is copper constant and copper nickel. So we have different types. We have we saw 3EJT. There is something called K type thermocouple, which goes to 1250 degrees centigrade. Then we have B-type thermocouple, which is made of platinum rhodium versus platinum rhodium. First metal is rhodium 30%, second metal is rhodium 6%. It goes to 0 to 1700 degrees centigrade with an accuracy of 0.5 degrees centigrade. We also have tungsten rhenium to tungsten rhenium, 5% tungsten rhenium versus 26% rhenium, which can go from 0 degree centigrade to as high as 2300 degrees centigrade. So that's called C type. So C type is 0 degree centigrade to 2220 degrees centigrade, tungsten rhenium 30%, and the other material is also tungsten rhenium, but rhenium is only 6%, because this is plus and this is minus. I have reversed it, it doesn't matter. So we have different types of thermocouples. So we already saw that if I have to use a thermocouple, I need to do cold junction compensation, right? So this is material B, this is material A, and we have the voltage, and we saw that the thermocouple wire uh, is of different type, nickel chromium, constant and copper, iron. So, and but normally the wires that we use are all copper, so we have to connect a junction. So if, let's assume this is iron constant, this is Fe, and this is Fe, and this is copper, right? When I put this again, this, there is a junction here, so there will be a voltage developed depending upon the junction temperature. But the nice thing is, if the temperature of this block is constant, right? So I will have plus minus here developed. So if theta j of this junction and theta j of this junction is also the same, and I see if this is V naught and this will be V naught, because if I go from here, that is plus theta j and this is minus theta j here. So so this is called as the laws of temperature. So if I have different junctions, and if my junction is at the same temperature, I do not get that affected. So the output V naught will be uh, proportional only to theta degree centigrade, right? Uh, so these properties are brought as laws of thermocouples. Let's look at laws of thermocouples. Laws of So the first law, we call it as homogeneous law. Law of homogeneous circuit. So if I have 0 degree centigrade, I am putting it as 0 degree centigrade. It can be instead of 0 degree centigrade theta 1 and theta 2, I will get difference between theta 1 and theta 2, theta degree centigrade. Normally for measurement, we always use theta 1 and theta 2, right? So it is immaterial. I can have theta x here, theta y here, theta z here, but the output voltage V naught will be only proportional to theta. It is independent of theta x, theta y, and theta z, the temperature on the wires. So if there is a temperature gradient, let's say I am measuring this at 1000 degrees centigrade. So this is 1000 degrees centigrade, and let's say this is at room temperature 27 degrees centigrade. So there will be a temperature gradient which will not affect our measurement. This is the beauty of the thermocouples. So we call this as law of homogeneity. Then the second law of thermocouple is law of intermediate temperature, intermediate metal, sorry. The law of intermediate metal states that if I introduce a metal, let's say uh, I have material uh, right. So now instead here I don't make a junction like this. I introduce another material, right? So as usual, uh, this is material A, this is material B, this is material A, and the output is V naught. Uh, I have introduced material C here, but if this temperature junction is at theta degree centigrade, and this we always say 0 degree centigrade, then V naught is immaterial of material C. It's whatever material I add, it doesn't matter. Again, because if I look at this, there will be a generated plus minus here and minus plus here when I go little. So this makes it very nice because a thermocouple junction can be formed the way you want. You can solder the thermocouple, you can braze the thermocouple joint, you can simply twist, make them join together. So that's one law that's very useful in preparing thermocouples in a very simple way. The third law of thermocouple is called law of intermediate temperatures. So the law of intermediate temperature says that if I have a thermocouple voltage, again this is A, this is B, this is A. Let's say I get theta 1 and theta 2. Then I have another, so I have E theta 1, theta 2, and I now put E theta 2 to E theta 3, right? I put theta 2 here and I get theta 3 here. Now if I put theta 1 to E theta 3, that would be E, I call this as E1 equal to E2. This will be E1 plus E2. Because thermocouples are linear devices, this stems from the linearity concept. So if I know the thermocouple output voltage for T1, T2 and T3, I can get T1 to T2, T2 to T3 and T3 to T1. So these are the three laws of thermocouples. Uh, by and large, thermocouples are very useful. The reason is, if you look at any other type of temperature measurement, every other type requires a large time constant. The time constant of a device we already know is if I put my temperature, this is time, this is theta step, the output of any measuring device will have a time constant, right? And if you look at the RTDs, they have time constants in terms of seconds. Whereas if you make thermocouple with very thin wires, normally 40 gauge or 42 gauge, then the time constant can be as low as 3 milliseconds, which is really small when we talk about measurement. The accuracies are also not very bad. As I said, you can get an accuracy from 0.5 degrees centigrade to as high as 2.2 degrees centigrade. Again, it depends upon the particular type of application. Uh, Even though we talk the linearity of uh, the thermocouples, they are not that highly linear. There is a little bit of nonlinearity. The nonlinearity can vary as low as 1% to 1% of full scale to 2.2% of full scale, depending upon what type of thermocouple we are going to use. So the biggest advantage of a thermocouple is uh, it doesn't matter how the junction is formed. So many times when you expect wear and tear on your material and you want to measure the temperature, then the thermocouple is the only solution. For example, when the space shuttle was launched and when the space shuttle returns back to Earth, it comes through the atmosphere at very high speeds, and part of the top layer is removed because of the friction in the atmosphere, and at the same time you need to measure. So if you have the space shuttle cone like this, and you want to measure the temperature here as the space shuttle enters, the thing is this is going to be on off as the space shuttle comes back. So the only way is that you put a thermocouple here and take that out. As the layer keeps varying, new junctions get formed, and you still have the thermocouple in action. This is another advantage of a thermocouple. As long as the junction is formed and the junction at a particular temperature, you get your thermo EM of EAB. So thermocouple based temperature measurement is quite popular for say various reasons, mainly because its smallness, because two wires, that's all it requires, and the reference junction compensation, right? I call this as cold junction compensation, which is kept at 0 degrees centigrade. We also call this as reference junction, right? So there are several ways of doing it. One is that you have the measuring thermocouple, and you have the reference junction thermocouple. So you keep this in a bath with ice plus water. So this will be exactly at 0 degrees centigrade. Or we can also take the and add the 0 degrees centigrade voltage. So in the past, this 0 degrees centigrade voltage was developed using a bridge circuit. So you can look at the bridge circuit reference junction compensation. We don't do it nowadays. We can generate this by using standard semiconductor voltage generation. So many modern thermocouples will come with inbuilt 0 degree compensation, so that you don't have to do anything on that front. So we look at the recap. Uh, we have learnt about the thermocouples. There are different types of thermocouples depending upon the materials A and B chosen. They are all given an alphabet name. J is iron constant, K, E, T, R, S, C, B. There are different types. The difference is in terms of the linearity, in terms of the temperature range, and in terms of the accuracy in measurement. Now, the thermoelectric effect is actually reversible. The reversible nature of thermoelectric effect was discovered by a person called Peltier. So it's known as Peltier effect. If I have a material A and B, and I send a current I through this thermocouple pair, the two junction temperature theta 1 and theta 2 will be generated so that the EAB here matches with EAB here. So that can happen because this voltage is plus minus, this voltage is plus minus. So if these two have to cancel, there must be a difference in theta 1 and theta 2. So generally theta 1, let's say, increases, theta 2 has to decrease. So this will be at a lower temperature, theta 2 will be at a lower temperature compared to theta 1 as higher temperature. This is can be used for both heating as well as cooling. Heating, it's no big deal, we can use a resistance and simply uh, send a current I square R, it will heat up, but cooling is very difficult. So this cooling is called a Peltier cooling element. You can buy them. You just apply a voltage to a Peltier cooling element, and it immediately drops down to 0 degrees, sometimes even minus 5 degrees centigrade, right? And this is one way of cooling electronic circuits. So some IC manufacturers make this Peltier cooling element part and parcel of the IC to cool the integrated circuit, and we use this all the time. Now, of course, I can now take a number of thermocouples. I can either connect them in series or connect them in parallel, which is possible, right? So whether I connect them in series or connect them in parallel, both is called a thermopile. A thermopile simply says more than one thermocouple is connected. It doesn't say whether it is connected in series or connected in parallel. Now, of course, we should understand why anybody wants a series connection or anybody wants a parallel connection. The answer is simple. If I want more voltage for difference in temperature, I connect the thermocouples in series, and if I want more current, I connect them in parallel. So sometimes this is also used to generate energy for other purposes. For example, the Cassini probe given by NASA, the internal circuits were energized using a thermoelectric generation using thermopiles. Uh, so far, we learnt about the thermocouple, and in the next lecture, we will talk about another miscellaneous sensor. Thank you.